I would like to introduce our presenters for this night school course, Ron Zemian and Craig Quadrato. Ron Zemian is a professor at Bucknell University. He received his bachelor's, master's, and doctoral degrees from Cornell. He is co-author of the textbook Matrix Structural Analysis, a developer of the educational analysis software Mastan 2, and the editor for the 6th edition of the Guide to Stability Design Criteria for Metal Structures. Ron is a member of AISC's Committee on Specifications. He chairs AISC's Task Committee 3 on Loads Analysis and Stability, and previously chaired AISC's Task Group on Inelastic Analysis and Design. He also serves on the AISI and Aluminum Association Specification Committees, is active with Steel Joist Institute, and the former chair of the Structural Stability Research Council. Ron has received many awards, including the ASCE Norman Medal and the ASCE Shortridge Hardesty Award. AISC has honored Ron with the Special Achievement Award in 2006, and last year he received the 2019 AISC T.R. Higgins Lectureship Award for his contributions to the profession related to stability analysis and design of steel structures. Craig Quadrato is a senior associate for Wisjani Elsner in San Antonio. He received a Bachelor of Science from the United States Military Academy in 1991 and has since earned master's degrees in engineering management from the University of Missouri of Science and Technology and in both structural engineering and construction engineering management from Stanford. He received his doctorate degree in structural engineering from the University of Texas at Austin in 2010. Craig was an active duty military engineer officer for 25 years, including serving as a construction engineer officer in Afghanistan, a member of the United States Military Academy faculty. In his current position with WJE, he heads the structural engineering practice in the San Antonio office, where he conducts assessments, investigations, and evaluations for existing structures. Craig serves as a member of the Structural Stability Research Council Executive Committee, chair of the SSRC Committee on Stability Education, and as a member of the National Student Steel Bridge Competition Rules Committee. Ron and Craig, it's a pleasure having you here to teach this course, and I'll now hand things over to Ron.
Well, thanks, Nate. It's great to be here. Good evening, ladies and gentlemen. I really look forward to this course and certainly representing the Structural Stability Research Council and the American Institute of Steel Construction. So I'm very excited. You can probably tell by my voice. I can't wait to get started. Let's check in with Craig. Craig, how are you doing tonight?
Ron, I'm doing well. I'm very excited to be here tonight. I'm looking forward to learning some great stuff, and just can't wait to get started here.
All righty. Well, let's get started. First thing I'm going to do is give an overview of the course. So let's jump in there. The topics are compression members. We'll spend 2 weeks on those. 1 week will be, the first week of each one of these will be more of the theory and behavior. And then the second week will be a lot of hands-on. And I'll be delivering the theory and behavior, 1, 3, 5, and 7. And Craig will be doing the even lectures that I think are going to be really cool. It's been a lot of fun. So we've got compression members, flexural members, a couple weeks on beam columns, and then we'll wrap it up with systems. One of the things that we're really looking to do is change the format a little bit on these night school courses, and especially this one with some active learning. So we're hoping that you'll participate, that you'll complete at least some portion of the weekly lab experiences. And we're also going to, have Craig not only showing us what he did during the week on those learning modules, but also provide some case studies. So one of the things I want to emphasize, though, is that this is going to be a little less formal. I'm hoping that on the odd lectures, Craig will pick on me, and I can't wait for the even lectures to pick on him and just, ask a bunch of questions that you might be thinking in the audience. So that's the game plan. Why are we studying stability? And I think that the starting point is when you think about the material, structural steel, you have to realize it has excellent strength to weight ratio. It has an excellent stiffness to weight ratio. But one of the real difficulties is that you've got to come in at a competitive price. And so when you combine the three of these, what you end up with are skinny things. You end up with a slender system, often slender members, and at times slender cross-sections. So all three of these things, anything that's skinny, slender, you put it into compression, and it has a real possibility of buckling. Hence, you've got to design for stability. When it comes to structural steel in general, I kind of think it's connections, 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 and designing for stability. But that's just my take. So it's a real pleasure to take a stab at trying to provide some background on the design for stability stuff. Our lecture series is going to focus on the fundamentals. We hope maybe this will whet your appetite for learning more. At least Craig and I and the staff at AISC and SSRC are convinced that a better understanding of behavior will always result in an improved design. So that's what we're trying to do, is really get you to understand the behavior, perhaps use some structural analysis software to play some what-if scenarios, all to just bring it together. Some key definitions that you're going to hear repeatedly, I won't go through the details here, but one of them is just stability. Something is stable if it's structure that's standing there and you can go up, you can displace it a small amount, it might bounce back and forth a little bit, but it will return to its original condition, and that's that. On the other hand, if we want to start thinking about how we get to an instability, then we sort of have two worlds. The first is the one that most of us were educated on, and that was, I'm not even sure the word was used, but it's bifurcation. And that is, it's a theoretical point, it's a theory here, it's a theoretical point in which there's an instantaneous change from the current state, the structure or the column or whatever you're looking at is perfectly straight, everything has happened, and then instantaneously 1 instant later, you see how I said that instant several times there, Craig, you move to you move to the buckled shape. All right, so that's the jump. So it's either not buckled or it is buckled. It's binary. It's bifurcating. On the other hand, what I'm going to call instability, and this is I think really the more realistic situation, and that is this structure is not perfect. It's not perfectly straight. The loads are not perfectly concentric, and as a result of this, as you apply the load, not much happens. As you apply more load, a little happens. And as you apply a lot of load, suddenly, gradually, that column, that system starts to deflect.
Ron, you got to draw me a picture here.
Okay, Craig.
You got to draw me a picture.
How about this?
Woo, that's it. I like it. Thanks.
You bet. So here is a plot of what I was saying. All right. So we've got on the horizontal axis the deflection. Maybe it's midspan of the column or the system. And on the vertical axis is the applied load. And if we're talking about bifurcation theory, the red curve, essentially you load, no deflection, you load, no deflection, and then instantaneously you go from a happy structure to a buckled structure. On the other hand, what I'm going to call instability theory is that you start with some imperfection, and that's what we're showing in green. We load, not much. We load a little more. Suddenly, that deflection starts to grow. We start losing stiffness. We start gaining deflections. We start getting more bending. We start losing more stiffness. And eventually, we will reach an instability. So there's two schools there. The green curve, if the assumptions are similar to the bifurcation theory, the green curve will asymptotically approach the red curve. So those are the two worlds. Now, Craig, the one thing that I want to emphasize with you is that timing, all right? When I say instant or gradually, when I say gradually with instability theory, it's still within, tenths or a half a second. It's not like a half an hour, all right? So clearly bifurcation is instant, but instability theory, a buckle can form very quickly, but it's in that very quickly time period in which we move along that green curve that I'm showing. So let's have a look at these analysis algorithms, because acronyms, sorry. We are going to do some analysis during this course. most of what's shown in red is what you've heard of before. Throughout the free world, there's been some acronyms that have been developing and being used, and those we want to start referencing in this course. So the very first one, LBA, this is a linear buckling analysis. We will refer to it within MassDan as a critical load analysis. A lot of computer programs provide this option. They're usually buried under the words an eigenvalue analysis. It essentially simulates a bifurcation theory. GNA, a geometric nonlinear analysis, well, that's your second-order elastic analysis. Okay, there we are getting equilibrium on the deformed shape, but it does not include initial imperfections when you run the analysis. GNIA is the same as GNA, all right, a second-order elastic analysis, but we do include the initial imperfections. Material nonlinear analysis is MNA. So this is first order. We've got equilibrium on the undeformed shape, but we are going to account for yielding. And then the one that's probably the most realistic, GMNIA, geometric and material nonlinear analysis that includes initial imperfections. So this is a second order inelastic. We do have equilibrium on the deformed shape. We are accounting for yielding, and we've got the initial imperfections there. So now, one of the cool things about introducing these to you is you can start using them anywhere. You know, you're out on a date or something, and you can just refer to Jimya, you know, and, you know, your partner will be, whoa, this person really knows what they're talking about. So, Craig, you got that down there,
yeah.
Jimya? Yeah.
I do. You know, Ron, I like to call this the alphabet soup slide here. We got a lot of, we need to buy a vowel in some of these.
Yeah, that's Jimya. That's Jimya there. How's my sound? Okay, Craig?
Yep, I can hear you just fine, thanks.
All right, good. All right, so that was sort of the course intro and a couple of details. And Craig and I are going to review those at the beginning of each one of our lectures. So we'll see that again. So tonight is all about compression members. I do have a lot of slides to show, so I'll have to move right along. So whenever you think about design, I hope you're visualizing limit states. All right, so I'm designing something. What are, in this case, the strength limit states? And for a compression member, certainly full yielding would be a possibility. Fine, we'll have a look at that tonight. Then there is the instability aspect of this, buckling. And tonight we'll focus on flexural buckling, but there are other forms, and I'll show a couple examples of torsional buckling or flexural torsional buckling. And then finally, if the section isn't compact, perhaps more slender, you could have local buckling occurring. So those are sort of the main stability-related limit states for compression members. And like I said, we're going to have a look at full yielding and flexural buckling. All right. Full yielding is the first one. Yeah, I know you're thinking, wait, this member's in compression and you're starting with a tension test, but yeah, we have to start somewhere. So remember that tension test that you did as an undergrad in your solid mechanics course? You took a steel specimen, a steel coupon, you stretched it, horizontal axis, you plotted strain, vertical axis, you plotted stress, and you pretty much got what's in the darker blue curve there, the stress-strain response. Now, the nice thing about structural steel is in the early going, up until we have some yield, you have a pretty linear behavior. You're in that elastic portion, and we can represent that slope with E. So we've got a real beautiful relationship, Hooke's law, sigma equals EE. Once the material yields, then things get kind of tricky. And what we have done in our steel profession and steel codes is we have assumed that the material will remain perfectly plastic. There won't be any strain hardening, and the E value, the stiffness of the material, has gone from something like 29,000 to something like 290, some small amount. So that seems to be where most of our code equations work off of, and we'll do the same. Now that's a tension test. One of the neat things about structural steel is that the properties can be assumed, very close and accurate in that assumption, that the compression behavior is very similar to the strain, to the tension behavior. So that response curve we can use again. And again, we are going to neglect strain hardening. So if all we had to worry about was full yielding, we could create a column curve. And some of you, this might be a new word, column curve. What the heck is that? Well, a column curve on the horizontal axis, we provide some type of slenderness. In this case, I'm just talking about L, but I'll revise that a little bit for the unbraced length of the column. And on the vertical axis, how much stress, P over A, how much squish can we put into that column? And if all we had to worry about was full yield, that would be our column curve. It would be that red horizontal line going all the way across, and no matter what the length was, we could load all the way up to full yield. And as you are already thinking, hold on, I know things buckle. A long, slender column, there's no way I could fully yield the cross-section without buckling it. And that's true, and that's where we're going to head. All right. A little bit about the buckling. We're going to focus on flexural buckling, and so it's predominantly the case, especially when you have doubly symmetric shapes like I shapes or HSS shapes, situations where the centroid and the shear center are at the same spot. On the other hand, if we go to the bottom right, in this case, the centroid and the shear center are not in the same place. And unless we load through the shear center, which is often not the case, we often always load through the centroid, we're going to get some type of bending as well as compression. And those things end up in a tricky failure mode in which not only do we have flexure, but we also have twist. And so we tend to call that flexural torsional buckling. And the in-between is that upper right, that cruciform section, in which when you squish something like that, you would get torsional buckling. So those are the three primary areas of concern, and we are going to be focusing on the flexural buckling side. Flexural buckling. So most people, and we will do the same, start with studying Euler's column. So I'll provide you, well, actually the slides are a bit off. I'll provide you the assumptions first, and then we'll have a look at the solution. But the way I'm going to get you to the bottom, that is the AISC column curves and the Eurocode column curves, is I'm going to piece by piece undo the assumptions that we had built in when we derived Euler's or Euler derived his solution. And so that's how we're going to go from Euler's column all the way to our, let's say, AISC column curve.
Ron, we're going to get to see some differential equations here?
That's correct, Craig. In fact, there was a pretest that AISC sent out, and yes, no. I might show you one or two, but no prerequisites to solve them. So relax, Craig, relax. I'm not going to send the consulting engineer dashing yet. All right.
Okay, I'll take a deep breath. Thanks, Ron.
Deep breath, Rick. All right, so first, Craig, I want you to know we're talking about Euler 1750s, okay? So Euler is not sitting there texting with Newton or anything like this. This is a time in which we do have pen and paper, but the pen is fountain pen, runny, inky stuff, and the paper looks more like bark than anything. So this is a long time ago. What do we have, 270 years ago? It's hard to believe. But what Euler did is sat down and he put out some assumptions. He said, well, I'm going to start with a prismatic member, and that basically means the cross-section doesn't change along its length. He's going to have a uniform, a fixed value for the moment of inertia. His deflections, once the buckling does occur, are going to be small. Prior to the buckling or bifurcation occurring, Euler is going to assume there's no bending. And the only way he can get there is he has to have the member perfectly straight, and he has to be concentrically loading it. The material is going to be assumed elastic, so E will be a fixed value, constant value. And then Euler went one step further and gave himself some boundary conditions that include a pin at the base and a vertical roller at the top. So Euler's world, that column was either not buckled, as I'm showing in the lower left or lower right, the left portion of the lower right, or we hit Euler buckling and then we buckled it. So Euler's is definitely a bifurcation solution. And so here we go, Craig. I'm going to set up those differential equations, but it's probably, I'm not so concerned about that, Craig. What I want you to realize is that every structural analysis, we do three things. The first thing is we write our equations for equilibrium, and that's what Euler did. And lo and behold, we wrote them on the deformed or the buckled shape. The second thing Euler introduced, which we do in every one of our structural analysis, is some type of a constitutive relationship. We relate force and displacement, stress and strain. In this particular case, it comes through relating moments to curvatures. So we have our moment curvature relationship. You substitute that moment curvature relationship for the moment into our equilibrium equation. Down lower left, you've got your differential equation, and Bob's your uncle, you can solve that bad boy, and that's what you get on the right. I said three things in every structural analysis. The third is a compatibility relationship. Euler's was simply at the top and at the bottom of the column, it didn't deflect laterally. This allows him to pursue all the way down to the lower right and get the Euler buckling load. It is a factor of n, okay, and we tend to focus on n being the lowest value, but so we're at Euler buckling being pi squared EI over L squared. But those higher values for n, well, it's one, they're nearly impossible to get to, because every time you go to load the column, it would buckle in the first mode. It would be hard to get enough load to buckle the second mode, because it would buckle in the first mode. But those higher buckling modes are interesting because they really point out, if you look where those inflection points are, they show a nice spot on where to put some bracing, a real efficient spot. So seeing higher buckling modes is actually a good thing. All right, so I'm going to take you now, well, I'll probably into the 1900s, in which we now have a column curve. The column curve can be made up of two parts. The shorter, stocky columns, full yield would control. And for longer, slender columns, Euler buckling would control. Now you can see I've taken the Euler buckling force and I've converted to an Euler buckling stress by introducing the radius of gyration, the square root of the moment of inertia over the area. So that would be it. It's a beautiful thing there, and we would be in great shape. We've got our column curve. We're ready to design structural compression members. So as part of this course, what Craig and I are going to try to get you to do is use some structural software. We'll be using Mastan, which is freely distributed, and will continue to be freely distributed long after the releases and all of that. So we're not trying to make any money or anything like that. We're just trying to provide you opportunities. Some of you would prefer to use your own structural analysis software, and that would be fine as well. So Craig, what I'm after here is I'm going to take a look, and I'm going to drop into Mastan. But before doing that, I'm going to do one of the cases. So I've got two columns. One of the columns, both of them are W14 by 145. They're oriented for minor axis buckling. So minor axis buckling will control. One of the columns is looks like just about 200 inches long, and the other is just about 600 inches long. If you can imagine that, I do have them inches. Yeah?
I'm not seeing your Mastan screen, Ron.
No, I haven't got there yet.
Oh, okay. Good.
It's not Mastan. I hope you're seeing my table.
I am. I got it. Okay. I was just a little out front there. Sorry.
No problem, Craig. We're coming. All right. So anyway, so we've got the two lengths, and if I divide them by R, I get a slenderness ratio, L and R, which is now the horizontal axis of our column curve. So I've got a fairly short, stocky column, L and R of 50, and a fairly long, slender column of an L and R of 150. And what I'm going to do is three different analyses: an linear buckling analysis, a geometric non-linear analysis, and a material nonlinear analysis. And then I'm going to take the smallest of those three values and divide by the area and see what happens. I got to get a stress. So in a moment, I'm going to head to Mastan, but let me just show you what you're going to see in Mastan. I'm going to have four columns for you. The two columns to the left are columns that represent the shorter, the more stocky L and R of 50. So those two columns have a length of just under 200 inches. The left one at the bottom left is perfectly straight, and the right one has a small imperfection, a sine wave, that reaches a maximum magnitude or amplitude at halfway up the column. So that's these two here. Right. On the right, I've got two more columns. They're both the same column. It's just that the column on the left is perfectly straight, and the column on the right has a small sine wave imperfection in it as well, and its amplitude is also ln 1,000. So that's what we're going to take on. The yield stress of this column is 50 KSI, and I've provided some other values. Py is probably one of the important values to note. That is the squash load. So if we take Fy and multiply it by the area, so 50 times 42.7, you will get 2135. That's the game here. A few more pictures. Once we go into mass 10, like I said, we're going to perform 3 analyses. The first one is a linear buckling analysis. This is an eigenvalue analysis. Most of your commercial programs will come with something like this. What I'm going to do is I have 1,000 pounds or kips. Sorry, I have 1,000 kips up at the top of this column, and I'm going to squish it. And when I do, my linear buckling analysis gives me a buckling applied load ratio of 0.5, 4, 3, 6, 9, all those digits. But that is telling me that roughly 54% of that 1,000 I could get on there, and right after that, the column would bifurcate. So that should be the Euler solution, 544. Now, if we run a second-order elastic analysis, right, on a column that's perfectly straight, what will happen is we'll start dumping load into that column, and when we reach that same 54%, what will happen is the analysis will not be able to converge. So we will get an indication that we've reached an instability. What we won't be able to see, regardless of how well we plot up the deflected shape, is we will not be able to see any form of flexural buckling. The imperfection is not there to grow. The only thing we'll be able to tell is that for some reason our structural analysis did not converge, and the reason being is because we've buckled the column. We do not get a picture of the buckled shape. So an eigenvalue analysis is nice because it does give you a picture of the buckled shape. All right? So that's the geometric nonlinear analysis of second-order elastic analysis. And then the last one that we'll do is material nonlinear analysis. So this is first order, so everything equilibrium on the undeformed shape, no second-order effects accounted for, and we'll start loading this column up, and we've got 1,000 on there, and we get to 2.13 of a load factor before all of a sudden we get all these bow ties on our structure. And those bow ties are, in fact, hinges, plastic hinges, indicating that you've fully yielded the member. And this is pretty much what we would have expected because 2130 was, again, Py, the full yield load of this column. And so those are the 3 analyses that we're going to do. And, Craig, I have now magically jumped over to my example 1. How does my mass 10 screen look to you, okay?
It's looking good. Yeah, Ron, that was smooth.
All right, so first up, I'm going to do so we're going to learn all about mass 10. My point tonight is just to, it's like taking you for a drive. We're out in the shopping parking lot, and I just gave you the keys, and go ahead, hit the gas, all right? Now, there's no one around, maybe one shopping cart you might bump into, but we got to start somewhere. So here I am. I've just opened up the model, and I'm going to do an eigenvalue or buckling analysis, elastic critical load. And the way mass 10 works is you pull from the top and you get your menu choices down at the bottom. And all I want to do is just run the analysis. So I hit apply for a planar frame. Again, I have oriented this column for minor axis buckling. And then using mass 10's post-processing abilities, I'm going to have a look at the buckled shape. And there I am. Go in and plot the buckled shape. And I'm looking down there, and I can see that column has buckled. And it has buckled up at the top. I read 4.89, or about 4.9 times that 1,000. About 4,900 kips I was able to get into that column before I buckled it. Now that's elastic buckling. Now I can do the same thing, like I said, with a second-order elastic analysis. I've got down at the bottom, I've got my increments on a very small amount, 1% of that 1,000. I'm going to run up to 1,000 of these steps up to a load factor of 5, and I hit go, and this thing is racing off. You can see the numbers changing at the bottom right there. And we're loading, and we're loading, and we're loading, and we're loading, and we're loading. Okay, 3,000. Okay, we're loading, we're loading. All right, we should be all right. And suddenly the analysis stopped and indicated that a limit load had been reached at, sure enough, 4930. Exactly what our LBA analysis had told us. If I go and plot the deflected shape, I can't really see much of anything. I'm not going to be able to see that buckle shape unless there's something to produce some bending, an initial imperfection or something like that. The last analysis is that first order inelastic or material nonlinear analysis. All set up down at the bottom, and I'm just going to hit go. And we're putting on the loads in 1% increments. And here we are, loading away. And suddenly, the analysis has stopped and said significant change in deformations. And what they're telling us here is, you've got a lot of deformation occurring. Most likely this deformation is occurring because of the yielding. And do you want to continue? No. So no, I don't want to continue. And so if I come in and I plot up my deflected shape, what I'm going to see over on the left is all of those bow ties, a whole bunch of bow ties. They're pretty large. Let's see, I could probably make them a little bit smaller so you can see them. Whoops, let's see. Display settings. Well, let's get those bow ties a little smaller so you can see them. There you go. So we got a whole bunch of bow ties occurring at a load factor of 2.13. We had 1,000 on there. And, well, that's what's going on. And so I'm going to return with those 3 numbers. I hope you've got them memorized, Craig.
Yeah, I got them in my head.
All right, so now the table's complete. All right, so if we take a look here, the previous slides gave me the results for the LNR of 150, 544, 540, 2130. I just ran live the LNR of 50 and got the 4890. Reran it with a geometric nonlinear analysis, got the 4930. People, 4890 and 4930 are the same number, okay? We've got a computer working here, so it's not going to be precisely the same. And then we have the material nonlinear results and the squash load being reached at 2130. So if we take a look at the shorter or more stocky column, LNR, of 50, the minimum load is 2130 divided by the area, and we're getting 49.9. So we have 50 KSI steel, so we're bringing this thing right up to squash. All right, so we are somewhere, if you can see my cursor there, right around here, and we're hitting squash long before we're hitting the Euler Buckling, which is about twice that amount. On the other hand, we're now out here with an LFR of 150. There, either the Euler Buckling or the geometric nonlinear analysis without an imperfection is turning off around 540. That's smaller than the yield. Divide the 540 by 50, and we get 12.26 KSI. So we're hitting the curve here long before we're hitting the 50. So that's what I was after. And that's the whole concept of Mastan, is to allow you, with a fairly simple program, to play and recreate results like this. All right, so that's as far as we've gone here. I'm doing a time check here. Well, not bad. I'm going to have to pick up the pace a little bit, but that's okay. We got to return to Euler's assumptions, right? Because right now the blue curve contains all of those assumptions. So let's go back to those. And the first one that I want to take on, or the first pair, is to talk about first the fact that the deflections are small after they're buckling, so we don't have this huge buckle occurring. And the second is that there's no bending. Right? So that's the first two. So let's focus on the bending issue. What could produce bending? Well, if there was an initial imperfection, the column was not perfectly straight, we will get some bending. Euler's column is perfectly straight. The other possibility is that the axial load is not coming right through, and in this case, the centroid. There's a little bit of an offset, some type of eccentricity, and that's going to cause a little bit of bending. All right? So both of these conditions exist in reality. We tend to always convert them all or say them all as, oh, the column's not perfectly straight. But even if you could get a perfectly straight column and you delivered it to the construction site, you can imagine the people with the white gloves putting it into place. The second you load it up, I'd be willing to bet my wallet, and there's a lot of money in my wallet, Craig. Anyway, well, maybe not. All right, so you don't want to make that bet. Yeah. We could bet a candy bar, and you'd be a lot better off. And there's going to be some eccentricity from that load, and that will produce the bending. So both exist, but we almost always call it an imperfection. And we think about a geometrical imperfection, but it's also a loading imperfection.
Yeah, when I order steel, Ron, I must be missing the box that says perfectly straight. That's what I want, right? There's no box there on that on the order form. Yeah.
Well, you're going to find another surprise in those columns in a minute. That not only are they not perfectly straight, but they've got another little punch back in them. So anyway, let's keep rocking. So I'm now going to try to go through the math fairly quickly with you of what if Euler had started with a column that was not perfectly straight. And I'm going to look at a column that has a sine wave built into it, and again with an amplitude of ln 1,000, the largest deflection, mid-length of the column, its length over 1,000. All right, so math gets a little bit ugly here, Craig, but basically I'm just putting equilibrium on the deformed shape, again introducing. So there's equilibrium equation on the deformed shape. I'm introducing my moment curvature relationship, and I've got that big gnarly differential equation. It's no longer homogeneous, but we'll now have a particular solution. Remember all that, Craig? Oh boy.
I do. Yeah. It's fuzzy though, Ron. It's fuzzy.
But that's okay. But what I just want you to know is once we solve that differential equation, we can actually get an equation for the deflection. All right. So we start with the original undeformed shape, deformed but with the imperfection. And then if we actually solve that differential equation that I'm showing you down at the bottom, the deflected shape, after applying some force, takes on this form of 1 over 1 minus T over PE. So if you want to move right to midspan, the deflection at midspan is whatever the original deflection was multiplied by this, I'm going to use the word, Craig, amplifier. All right? Some of you already think, wait, that looks like the B1. Hey, you're getting ahead of me. But that is an amplification factor, 1 over 1 minus P Euler. And that is exact, all right, theoretically exact. Now I'm going to return to this slide that I showed earlier in which we're loading the column up. We're not going to bifurcate the column because it's not perfectly straight. If we were to, we'd come right up to Euler buckling and raise across. But instead, we've got that imperfection in the column. And at first, not much happens. But as we get force into that column, P starts to approach the elastic buckling. The term in the denominator starts to get small. And when it does, 1 over that starts to get large, and we start to get quite a bit of amplification on the deflection. The deflection really grows crazy. And so what do you do? And what we tended to do in AIC is we sort of put a limit on the amount of deflection that we're willing to tolerate. It's not a number, but it's a feeling. And so what that means is we're not going to allow you to get all the way up to the full buckling load. We're going to allow you to get up to, I know, Craig, you already one ahead of me, 0.877, but around 80, high 80s, low 90% of the Euler load. And by the time we get there, we're going to have quite a bit of deflection in this column, and we'll cut it off there. So we don't typically allow you to go all the way up to the full Euler capacity.
So Ron, if I understand what you're saying, then the initial imperfection doesn't necessarily affect the final buckling load we could theoretically get. but we really practically just have to cut ourselves off somewhere when the deflection gets so large.
Absolutely, absolutely. And in fact, I'm going to illustrate this by taking that same 14 by 145, and I'm going to let you guys play in Mastan, but I'm just going to drop and show you some Mastan slides, what you could do. And so I've built in the initial imperfection, and once I do that, I run now the second order elastic analysis just like I did before, but I've got an initial imperfection built in there. And using Mastan's plotting facilities, which you can learn through by completing the tutorial, what you can get is a plot that shows the lateral displacement, say, of this node, the x displacement, as I applied the load. And look what happened here, Craig. It seemed like I could get a hell of a lot of load in there, but I've got deflections on the order of 50, 100, 150 inches. This column was, just under 600 inches long. So the deflection, let's just say you would be running for the hills there, Craig. You saw these deflections on the column, all right? And by the way, do you guys have any hills down there in San Antonio?
Yeah, we have some small ones. We're right at the foot of the Texas hill country here, so I can see some hills.
Okay, good. Because I wouldn't want to use an expression that, technically wasn't correct for you. All right, so what we're going to do here then is we're going to limit the elastic bending deflections to some amount, and the way we're going to do that is we're going to curve how much of the Euler buckling we're going to let you get to. And so I'm going to call that alpha here, and what you will see later in the presentation, and many of you know, AISC has set that to be about 0.877 or some number around there. And we can talk about why 3 digits and all of that in a bit. But, so the problem, though, is we're doing okay. What about, well, let me think. I think I have another slide. Okay, yeah. So let's jump here, and let me just illustrate this with the 14 by 145. And I'm going to build in that initial imperfection, and I'm going to say, all right, 6 inches of lateral deflection in that column, that's a lot of deflection. I'll be able to see that for sure. I would be very nervous. And when I look on my plot, 6 inches occurs somewhere around 500 kips. All right, so just, again, how one could use a curve like this to sort of define the capacity of the column. And so 500, divide that by the area, and I'm coming in at a value of about 11.7. Right? So the initial imperfection took me from 12.6 KSI down to 11.7. So that's a number around 90% or so. Okay. So one of the issues that we have is that we've been assuming that the material is linear elastic, that there has been no yielding. So, okay, we know we're going to get some yielding. So how do we modify Euler's solution to account for some yielding? Let's talk about this yielding. I'm looking at a column here in which it's being subject to major axis bending. Just major axis bending, and this is a very short stubby column, and on the horizontal axis I'm monitoring the rotation, and on the vertical axis I'm monitoring the moment that I'm dumping into this thing. All right. At first, this section behaves pretty well, MC over I. You can see the stress distribution here. Everything's elastic, but essentially I'm going to reach the point that MC over I reaches yield. And once I get yielding up in the top and bottom, I lose the material stiffness. So the column, the bending member, has a smaller amount of elastic section. As a result, it loses its stiffness. Once we fully yield those flanges, all we got left is the web, and that really hurts when we eventually get to a plastic hinge. On the other hand, if we were to look at things with minor axis bending, it's a little bit messier because the flange tips are really providing a lot of the stiffness. So once we yield those flange tips, we start getting a lot of deflection, a lot of rotation quite quickly. And once again, though, we'll reach the plastic moment capacity. So But Euler's world is all down here. The reality is because of that bending, we're going to be up there. Now things get a little bit tricky. Not only do I have bending, but I'm also applying some axial force, some compression. So you might recall from your undergraduate days the stress out at those flange tips is P over A plus MC over I. Right? So we've got a little bit of axial force and a lot of bending, and this is pretty much what the response curve would look like. Again, you've got more yielding on the compressive side of the member and less on the tension side from the bending because the compressive force is there. Eventually, again, you will reach a plastic hinge, but it's a combination of the axial force and the bending, and you will not be able to get to MP. More axial force, so a moderate amount, not just a small amount, and this curve dramatically shifts downward. And then columns are a lot of axial force. And so here is a situation where we have a lot of axial force, and what I'm trying to show here is it does not take much bending before we get yielding, and once we get the yielding, we blow out the column. So bending hurts us in a compression member, and the bending is going to come from that initial imperfection or that concentric load. All right, so a small amount of bending can quickly lead to a significant amount of yielding in a heavily loaded compression member. So that's an important point. All right, so I'm going to take a closer look at the bending now in the column. And so I do have the solution from before for the deflection. I know that the bending is 2 derivatives higher, so I can actually compute what the bending moment is anywhere in the column that has an initial imperfection. And that's what I'm showing down at the bottom. And as you would expect, there is that moment amplification factor that we were talking about. And before, it was appearing as an amplification factor from the deflection, but it's still alive. Right. Here's just a fun slide that you could quiz your buddy with, and that is how much axial force could I get into a column that has a small initial imperfection before I would yield it. And so we're solving for P in this equation, and it'd be kind of fun to solve for that. Now, this equation doesn't include the possibility of some residual stresses, and we'll talk about those in a moment. So what's going on in this column that's not perfectly straight? Well, we load, we get some bending, we provide some more compression, eventually we yield the column. Once we yield the column, we lose stiffness, we get an increased amount of lateral deflection, more bending moment, more yielding. Hopefully we reach equilibrium and we're allowed to continue loading, but eventually we won't be able to reach equilibrium and we will have fully blown out the column. So that's how an instability actually occurs in a real-world columm. Yeah. So these curves that I was showing you before, the blue curve, where we sort of asymptotically approached the Euler curve, we can no longer get there. We can't even get close to Euler now because what's happening is we're getting some initial yielding, which is enveloping into a full, inelastic failure of the column. All right? And this occurs at low column slenderness ratios. All right? So if the slenderness ratio is fairly small, we're here. All right? We've got a curve now that we cannot get to full yield. We're going to get to something less. We'll talk about what something less is in a little bit. So we've made quite a bit of movement in getting ourselves from full yield. That was red. The blue dash was Euler. Then we brought in Euler to account for the initial imperfection. Now we've got bending eating our chips, and so we're losing strength. We've got partial yielding occurring, and we're there. Now, the one thing that we haven't accounted for yet that's going to accentuate the partial yielding are some residual stresses. So let's go there. What are residual stresses? Well, here's a very busy slide, but I'll go to the next slide and give it to you in pictorial form. But what happens is when you take a shape and you roll it, it's piping hot, and when it cools, the cross-section does not cool uniformly. The portion of the cross-section with more surface area cools first. It sets. The remaining portion wants to cool and contract, and it can't. and you get into some interesting response. A couple important thing to note is the residual stresses are usually almost always independent of the yield strength of the material. We tend to say, oh, they're about 0.3 Fy or 0.5 Fy, and I'll show those slides in a minute. But once we go to the high-strength steels, that is not the case. All right? They're a pretty fixed number. And when we rotary straighten them, we tend to, or even just more emphasis on using near net sections before the rolling even starts, we tend to have much smaller residual stresses, if any. So here we are. We've just rolled a wide flange shape. I was down in Blytheville, Arkansas, at the Nucor rolling plant. It was like standing next to the sun when these roll shapes would come down, and they put them aside to cool, and you can see the differential cooling occurring between the flange tips and the web. And what we get is some interesting action. Like I said, those flange tips, they cool first. They set because they have a lot of surface area. The web flange intersection cools later. And you end up with, when it wants to cool, by the time it wants to cool, this one has already cooled. The E is at full 29,000. It wants to contract, and you end up with sort of a push-me, pull-me. That reminds me of, what was that movie? Dr. Dolittle. That was it. Dr. Dolittle. The push-me, pull-me is some type of llama or something. But, all right, I'm totally off here, Craig. Sorry. But you end up with a portion of the cross-section in compression and a portion in tension. Right? And the actual distribution looks something like that. Or here are some pictures. It varies how much that residual stress is from cross-section to cross-section. And, of course, whether it was rolled or welded can impact the residual stress platform. So it's a complicated subject. And the point I want to show you is these residual stresses are not small. They can be the order of 30 to 50% of the yield strength. All right? So remember, Craig, when I was telling you, you thought you bought a perfectly straight column, you realized you didn't. You also bought a column that may have some residual stresses already built in it. These residual stresses cause yielding to occur much earlier, and that's not necessarily a good thing, because once you get some partial yielding, all right, you're losing stiffness quite quickly. So now this is a sub-column test, and I'm plotting on the horizontal axis the squash, the change in length of the column. Upper right is the sub-column itself. And so I've got this normal strain in the column, and on the vertical axis I'm plotting the stress, and because those residual stresses are there, we will get a nonlinear response curve. Years back, I'm thinking in the 1950s, 1960s, I believe the foundation of this equation came out of the Lehigh research, and they found a very nice model that actually replicated what they were seeing experimentally. And that was, if you started with the yield, subtracted off the residual, and if we were willing to call the residual stress 50% of the yield, that would happen as you were loading the column, now at 50%, and you would go from a nice happy E value to a reduced E value. And the reduction factor is what we call a tau factor. So Craig, have you ever seen that tau factor anywhere before?
That one right there?
That one?
Well, I'm kind of scratching my head. No, I don't think I've seen that one.
All right. Well, we're gonna ride this one out together. If you visit Chapter C of the AISC specification under the direct analysis method, you got a 0.8 on tau. This was the tau that our group finally landed on. And when we put out the direct analysis method in the around 2003 or so, we were running this equation before it got printed in 2005. Anyway,
great. So we'll talk that a little bit later, and notional loads too. I know we'll throw in there too, right?
Yeah,
for some of these things.
Yeah, that's all coming. Lectures 7 and 8. Yeah. All right, so I'm into some rotary straightening now. This is occurring almost at all the mills. Again, the mills are using the rolling mills are using near net section, which means they're very close to. There's not a lot of rolling that needs to be done. And then if the member still isn't nice and happy and straight and meeting the code of standard practice, they will run it through a rotary straightening process. And they can rotary straighten some very big sections. Now, what's interesting is they are physically bending the shapes straight. They have to yield them and then unload them. And when they do that, they relieve the residual stresses. So rotary straightening is definitely helping remove a lot of the bad news. All right, so now, if you take a look at the top here, I could return to Euler, but instead of using Euler's elastic modulus, I could use the E sub t, the tangent modulus, being reduced by the tau factor, and when I would plot this up, I would actually get this green curve. And that green curve is what was in our AISC specification for the strength of a column, oh boy, probably right up until 1986 with the introduction of the LRC and the new column curve. So this column curve in green was certainly acceptable, but there's still a bit more knockdowns that we take on it. So here's take 5. We're going to have a look at a W14 by 145 now. We're going to run an analysis that has everything in the kitchen sink in it. All right. So we're going to have the initial imperfection. We're going to formulate equilibrium on the deformed shape. So we're going to grab that. We are going to account for partial yielding and residual stresses, everything, and we're going to see what kind of capacity we get. Now, I've already looked at this column twice. If I only considered the full yield, no initial imperfection, I could get to 2135, both columns. If I did a geometric nonlinear analysis or a linear buckling analysis, I could get to the Euler load, 4930 or 540. Now what I'm going to show is that we've got everything there. We've got the initial imperfection, we've got the residual stresses, we've got the partial yielding, and we have the geometric nonlinear effects, the equilibrium on the deformed shape. So let's do this one first up here, and then I'll drop in and run the analysis. So here we are doing a Gymni analysis on that tall, slender column. I've reached, the analysis kicks out and shows me the actual buckled shape at 46% of the load. So I've got 1,000 on there. So I can get 460 into this column before I fail it. All right? And this is just using, a computational software, which is attempting to account for all of those effects. All right, so let's see. I'm going to come over here, Craig. I'm going to change this back up so you'll be able to see it. So let me put that back up. There we go. I need to put some load on my column here. So forces, let's zero out all the columns. And on this column now, Craig, I'm going to put 1,000 minus 1,000. All right. Craig, can you see it okay?
I can, yeah. And the units here have to be consistent, don't they, Ron? Because MassStan doesn't have units. You just have to make sure everything's consistent when you put them in.
That's right. So really, at the beginning of the day in MassStan, you make a decision. What am I going to use for the modulus elasticity? And if you say I'm going to use 29,000, the units have been just defined for you. I need to make sure all the forces are in kips, all the member lengths, all the element lengths, all the geometry is in inches, section properties, moment of inertia, inches to the fourth, moments applied, kip inches. You just need to be consistent. And then your results will be also in those consistent units. So, yeah, good point, Craig. So like I said, I'm going to run a second order inelastic analysis. That column down there, Craig, that I got the load on has a initial imperfection. And so I'm going to do a Gymni analysis. Pretty exciting here, Craig.
All right. Yeah, that's our first one. First one for the course, right?
Yep, here we go. Now, one of the things, Craig, for me to account for the partial yielding in MassStan, I've got this modulus, and it can be set to many different values. And as tempting as it is to use the AISC tau value, I'm going to just use that ETM, which is one that we developed to more accurately account for the partial yielding. All right. And let me hit go. And so here we are loading that column up. Let's see how much load we can get in there. Oh, okay, so the analysis is stopped. We have reached a load factor of 1.710, and let's take a look at the deflected shape here. And not very dramatic, okay? The column is just, well, it's dying due to the partial yielding, and we're getting some buckling there. I'm not sure if you can see it there, Craig, on your screen or not, but yeah. So we lost this column at a load factor of 1.71 times the 1,000 should put us at 1710. All right. So let's see, yeah. So in the slide, I showed you how we could get to 14,460 for the long column. For the shorter column, I got that load factor of 1.71 times the 1,000 or 1710. So let me get a sip of water here quick. When I divide by the area, the Gymnia results, Mastan has cooked into it. It has calculated the strength of our column. And at an LNR ratio of 50, our column has a strength of 40 KSI. At an LNR ratio of 150, it has a strength of just about 11 KSI, 10.8. So that's, you know, we haven't used any column curve out of AISC or anything. It's just that programs like Mastan that have the ability to do a full geometric and material nonlinear analysis that accounts for partial yielding and initial imperfections, they can predict the strength of the column for you. And in this case, for an L over an R, we're somewhere around here, we're hitting the green curve at 40 KSI instead of the full 50. Out of an L over an R of 150, we can only get to about one-fifth of the strength of the yield strength of the material. So, yeah, kind of interesting. Now, part of the learning module that I'm hoping you'll attack over the next week is to actually do a study similar to this one. Now, in this one, I used some pretty sophisticated shell elements, but you should be able to get similar results with Mastan. And what I'm showing here is for that 14,145 is on the horizontal axis, the L and R, and on the vertical, I've taken the stress in the column and normalized it by the yield. And I'm just kind of showing you, we started with full yield, we did Euler, then we just included the initial imperfection, but did not account for the residual stresses and the partial yielding, and then we went with the full Gymnia analysis, and we ended up with the red curve. And so our LNR of 50 was around here, corresponding to the 0.8. 40 KSI failure that we're seeing, 150 corresponding to the 20%. So that's what we're doing. Some key observations: yes, the strength is reduced for the initial imperfection, and it's further reduced as a result of the residual stresses and the partial yielding. All curves approach Euler, but it's slightly below. Partial yielding really eats our lunch with respect to minor axis versus major axis. And we could have different strength curves for major and minor. And so these thoughts is that in reality, every single Y-plane shape at every single length has a different column curve. Okay, or every different Y-plane shape has a different column curve. All right, and that's not only just the Y-plane shapes, the HSF and all of them. So if we were to plot up, as Radolf Yehovda did in his PhD work at Lehigh in the early 70s, you would have a Milky Way of column curves, each column curve reflective of a particular cross-section, maybe some welded together, others not. Right? So we need to sort of move from the Milky Way into a design equation. Right? So I'm going to show you the AISC column curve. It employs a single fit, and we have both the experimental and the analytical data. And if you really want to roll up your sleeves, one place is to go all the way back and obtain a copy of the Yehovda's PhD work. It was very impressive. But it was really in 2001 that Ray Tide kind of showed his cards, and he said, look, in the early 80s, in all honesty, I took Yehovda's research and I fit the column curve that appeared in the 1986 LRFD manual, the LRFD specification. So it was really Ted's curve fitting that allowed us to have two equations that were continuous, and to get them continuous at that point that Raytide was after, I keep saying Ted, Raytide was after, was where these 0.877s and stuff came to. We also provide some background in our guide, SSRC's guide to the disability design criteria for middle structures. Now, Raytide, that should sound like a familiar name to you there, Craig.
Yeah, it does. Absolutely does, yeah.
Yeah.
WJ
he's
guy.
with Jenny Elster.
Yep,
Isn't he with
right.
your company? Yeah.
Yes, he is.
Just a wonderful person if you get to meet him. But all right, so here we are. This is the AISC column curve that sort of goes right through the middle of the data. And for lower slenderness, it's this 0.658 to this crazy ratio. And for larger slenderness, more slender column, it's 0.877. And that sigma E, that is indeed Euler's equation. So Euler 1750, and it still appears in our AISC specification today. So that's and other specifications worldwide. So it really, Euler got some mileage out of that one. I thought you might be interested in seeing what happens when we put the 14145 finite element results, again, hoping you'll do these, some of them as part of this week's learning module. The AISC column curve sort of sits right in between major and minor axes finite element results. And it's kind of cool to see where it's going on and what we had to do. But again, you would get two different curves, whether you were subject to the major axis buckling or minor axis buckling. And the reason for the two different curves is because partial yielding with those residual stresses there are much more significant for minor axis bending than because you lose the flange tips. Once you lose the flange tips, this thing's coming apart. I mentioned that there are other column curves. Eurocode is one of them. What I just want to show you with Eurocode is over on the left, you can see they actually have 5 different column curves they use, and they use those 5 different column curves depending on the section. You know, there's all different sections. You would grab a different column curve, the bending axis or the buckling axis, and even the depth to width ratio of the column. So for the column that I was looking at, 14145 in this lecture, for major axis, I would have the column B here, and then for minor axis, I would use the C. And that is really quite consistent with that finite element analysis results. So they've taken it a level further. AISC has decided to just have a single column curve to represent all shapes, and that's the way it is. It's fine. One last thing here, we made our way through Euler. Our last stop is to have a look at those roller supports, pin roller down at the base. Rarely is that the case in design. Maybe in a truss, you could say, well, pin-pin connections, but in any type of a frame or something, it's really hard to find a pin roller support condition. So we need to account for other possibilities. Just looking at the column, you could go to the commentary of AIC, and you'll see this table that shows you all the different possibilities, the different amount of end restraint. From the left, both ends restrained from bending, to here's our Euler column, pin, pin, here's a cantilevered column. And so we've got all kinds of combinations to look at. To figure out what the load is in each one of those columns, one could, once again, roll up their sleeves and solve the differential equations. You could be a modern-day Euler if you wanted to. Here's the case with the fixed base and the pin up at the top. And I just sort of show you the math on how to get there. And down at the bottom, we don't longer have capital E as in Euler, but now lowercase e as in elastic buckling. And you would end up with a 0.7 L squared. And that 0.7 follows through as the K factor for this particular column. So there's an introduction to you where the K factor is coming from. All right. So for elastic buckling stress, we move from Euler, which is pi squared E divided by ln r squared, to now pi squared to the elastic buckling stress, which accounts for the end conditions, and we introduce a K factor. And across the bottom are the different K factors for the different conditions. Sometimes you don't have those conditions, but you do have a deformed shape. I think the rule of thumb, if you're trying to visualize or even come up with the 0.7 or the 0.5 for your K-factor, is, sketch the deflected shape, sketch the buckled shape, and in your sketch, look for the inflection points where one side goes from compression or tension to the other side, and the distance between the inflection points defines the KL, or the proportion of the Euler column. All right? So it's kind of a fun little exercise to do, is to locate that distance between inflection points. Craig, I'm going to just take a minute here and talk a little bit more detail. Before I jump right into mass hand, I'm going to take a breather here from all that theory and just talk to you a little bit about these learning modules and what I'm trying to get you to do next week, Craig, as part of your homework. And that is, I develop these things. They're like virtual laboratory assignments, all right? And they focus on stability problems. I would love to take you into a big structural test lab, but we can't do that. And so we're going to do it on the computer instead. And the concept is, again, to better learn structural stability and have some fun while doing it. Nobody's going to get hurt. You're just going to run some analysis, and, it should go pretty well. So it's a hands-on, active learning. You get to do a lot of what-if scenarios. Like I said, it's software independent, but I found that Mastan does the trick, and you might as well. Each one of the learning modules, I think I've uploaded 3 now on the site. All are in a consistent format. I first provide an overview, what the learning objectives were, what the method is, some hints, some questions, some details if you're using Mastan, some assignments, and then if that's not enough, then I give you a more fun section, even some more questions to wrestle with. So everyone from the novice to the one that's been doing this for years can really put it to the test. The resources, I provide spreadsheets for you to fill in your results, but I've also got a lot of tutorials online, YouTube videos that show you how to do things like build in an initial imperfection in a column or the like. So it's all there. Like I said, they've got these YouTube videos. This time, looks like I got a relatively new screenshot in there with 12,700 views. The first time I had this slide I showed for years, it had like 11 views, but my daughter would tease me relentlessly. I'd tell her, I went viral. She says, not with 11. No. But the learning modules all focus on using very simple Mastan 2 or whatever program you're using line elements. All right? They're not using the shell elements like Adena or Abacus or ANSYS would provide you. So I'm over on the right here. The analysis are very quick, very easy to create the computational models, but they give really good results. We've got 9. We are going to experiment with several of them. Your assignment this week, Craig, is to complete number 2, and that is to do a study similar to what I did during this presentation, but have a read on that learning module about the factors that influence flexural buckling strength. For example, initial imperfections, how much does that happen? How much does it influence the strength of the column? The one I'd like to look at right now was the elastic column buckling and the effect of end restraint. Where I'm going back to, Craig, is I'm going to take a look at that series of columns that I showed earlier on that were in the commentary, all the different end restraints and the different K factors you would get. Now, if we were in the classroom, what would be awesome is if each student could have one of these contraptions down here in which they could vary the end restraint on these very thin columns, and then they could stack steel weights, and they would be able to see which one of the columns could hold the most steel weight, and you can see the proportion. So it's just a beautiful teaching tool. Unfortunately, we don't have 200 of these to distribute to all of you, and I have 1 in my classroom, and I really want my students to roll up their sleeves and have a go with it. So I created this particular learning module with that in mind. All right. So let's see. Yeah. So let's. How are we doing for time? We're pretty good. I'm going to Well, let me just jump over to Mastan, open up that model. If it's too cumbersome, I'll bail. But,
so, Ron, I can go back and do this. This is Learning Module 1, right? Is that what you said? So we can go back and do this if we want to for ourselves, yeah.
Yep, and I provided you folks the file that I just opened. So there's not a lot of effort involved. You basically run the buckling analysis, elastic critical load. I'd like to see the first 10 modes. You'll understand my madness in a moment. And to let it run, and I mean, today's computational tools are so fast. Plot up the deflected shape. So this is the first mode, and you can see, sure enough, the column that was fixed at the base and free, the cantilevered column, buckled at the smallest load. I have one kip on each one of those columns, and so the load ratio to buckle that was 273. So that's how much it would take to buckle this column. I'm going to jump back and just show you. So that's that one, and with that mode and its corresponding, we can back calculate. We got the elastic buckling equation. We can back calculate for the K value, and sure enough, we would get 2. And so we can keep marching. Similar, fixed at the top, but pinned at the bottom gives the same number. And just like AISC is showing a K factor of 2. That's the second buckling mode. The third buckling mode is the Euler mode, and we'd expect a K factor of 1 there. The fourth mode is actually the same value. This is the lateral fixed case. So the K factor still is 1. The inflection point is somewhere here. And if we go upward all the way, well, right off my screen, back in the same spot. So the Euler length is still the length of the column. So mode 5 is here. That was the one I derived for you with the differential equations, K factor of 0.7. And then it's kind of fun. We still haven't got the far most left column yet. So we got to work a little bit. We go through mode 6, mode 7, mode 8. And finally, in mode 9, we get the fixed case. So when you have a K factor of 0.5, you increase the strength of the column by a factor of the Euler strength. We increase Euler strength by a factor of 4, and that's what you'll get to experience. Important to note that I have subdivided the column up, in this case, into 8 elements. I do that because I'm using cubic elements, which are quite popular in finite element software, and I need a few more cubics to model a sine wave or a sine and cosine wave. So that's why I do that. All right, so the K factor really is a function of the amount of end restraint. We looked at a bunch of simple cases, but as you can imagine, when you move to more complex structures, what is the correct K factor? You've got to do some work, and we're going to talk about that later out in Lecture 7. All right, but so there's ways to get there, alignment charts. Be careful, and we'll talk about why to be careful. And then, of course, you can completely bail, use K as 1, and just employ the direct analysis method. So some fun there. So we've done it here, Craig. We've got ourselves to an AISC column curve that I'm showing down at the bottom. It's a 2-part curve. The part to the left, the more stocky columns, where inelastic buckling will control. The part to the right, where elastic buckling tends to control, and for more slender columns. So we have done it. We had started with Euler, and then one by one we undid the significant assumptions. We did keep our columns prismatic, but if you want to go for the more advanced course sometime, we can go with tapered columns or what you have. Sorry, I had to take a sip here. So let's put things down here. I gave you a course intro. We talked about general concepts of stability, bifurcation versus an instability. We looked at limit states of compression members. We started with Euler buckling, and then we systematically moved to a column strength curve. That curve needed to account for the realistic possibility of a really short stubby column, which would get to full yielding. It needed to account for bending, which could be due to initial imperfections or non-concentric loading, partial yielding, it hurts, and it even hurts more if there are residual stresses there, and also some degree of end restraint. I showed you the AISC column curves, but I also showed you the Eurocode curve, which tends to be adopted not only in Europe, but in Asia, in Australia. They use a very similar multiple column curve approach. I also subtly try to introduce you some concepts of a moment amplification factor, a stiffness reduction factor, and I also hinted at the complexity of trying to get a K factor for anything other than those very simple pinned, fixed, or free boundary conditions on the end of our column. So I'm hoping, Craig, that not only you, but our attendees, our students, will try and complete at least some portion of a virtual assignment. Perhaps they just start up MassDan and try, or their own program, and try to recreate one of the examples from this lecture. If they check out Learning Module 1, they will see that was the second example I showed. So they've got the models. All they need to do is run it and confirm they can get the same results. And what would be great is if they could go in and just run a few of the cases, the more the merrier, for Learning Module 2. So that's the assignment, Craig. How are you feeling about that? You ready to take it on?
I'm ready, Ron. I'm ready. I do have one quick question here at the end, and it looked to me like that AISC column curve might be a little bit unconservative in some cases. Is that something we should worry about?
No. Quick answer, no. There's a lot going on, and I think I'd like that deserves some pictorial representation of where it's unconservative and the like. Probably something we can talk about next week once you've had a chance to look at Learning Module 2 and get some results. We can talk about where things might be at least appearing a bit unconservative in how we're handling it. But I think I'm going to.
Okay, great.
I'm going to hold you off until next week. All right.
I like a good cliffhanger. Yeah, that's great.
a good cliff. Yeah. Yeah, you won't be able to sleep now for the entire week. Of course, they're going to be like, "Whoa, what is it? What is it?" But having been born out on Nantucket, I always like to end with something related to sailing and the like. But here we got buckling like Indian canes in a land of tornadoes. Whew. There you go. I guess you were Army, you weren't Navy there, so I don't know. Did you ever see a boat or anything, Craig?
Yeah, I saw them. They were out there somewhere.
Anyway, I'm Nate. I'm going to turn it back over to you. Sorry for going a bit long, but more than glad to answer any questions or follow your lead.
All right. Thanks a lot, Ron and Craig. That sounds good. So I'm going to direct the audience's attention to the welcome window, and we're going to pull up a poll question that we are going to pose to the audience here, which you should see here in a moment. So we're first going to do this poll question. The audience can participate by selecting the answer they believe to be correct. So this poll question is as follows. Small amounts of bending can occur in compression members because of which of the following answers? A, initial out of straightness. B, residual stresses. C, non-concentric axial load. D, both answers A and B, or is it E, both answers A and C? Again, small amounts of bending can occur in compression members because of which of these following answers? So go ahead and select the radio button on your computer screens for the answer you think is correct. And let's see what the results are. We're going to close the poll here. All right, Ron, we have some interesting results here. We have 83% checked in with E as being the right answer, which is both A and C, initial out of straightness and non-concentric axial loading. And then pretty much everybody else, about 16%, thought the correct answer was D, both A and B. So what were you looking for here?
Yes. Well, thanks for the question, and I'm real pleased to see so many people went with E. Certainly, even those that went with D realized that the initial out of straightness was one of the culprits for producing that bending. The other was just having a small eccentricity, the axial force not going through the centroid, but a little bit off, and that can cause an eccentric moment at the end and cause some bending. At least the way I presented it, the residual stresses weren't actually causing the bending. What they were doing is tending to accentuate the partial yielding. So A and C, and well done.
All right. So we're running a little short on time here. Let's try to get to some questions that came in from the audience. And I'm going to start back by going back to slide 5. Again, we're staying in the welcome window there. Actually, I'm going to go to slide 6 for these first questions that came in. And I think, Ron, you got to this a little later, but we had a number of questions right away, and I think it might be good to go back to this overall overview slide. Yep. The question is, one question asker says, what does this instability actually look like in a column on the instability theory curve? And another question asker says, does this slide mean that after exceeding a critical load that the column will actually not be buckled at that point? So I think they're trying to home in on this instability theory. Sure.
Well, let's see. Let me try my best on what's happening to the column is. Let's take the question really is focusing around the instability theory curve, the green one. So we have a column that has an initial imperfection of ln 1,000. It is so small, Superman couldn't see this. Right? It is tiny. I'm told that the initial imperfection that you could see would have to be something on the order of ln 300 before you'd even be able to pick it up. So this is a very, very small amount of initial imperfection. We start loading the column, and we're watching the column in the lab with this very small amount of initial imperfection that we can't even see, and pretty much nothing is happening. We can hear the machine running louder, more load, and suddenly, just visually comes into it, we can see the bending of the column. All right? Load it up a little bit more, and then finally, we stop the test because the bending is on the order of 6 to 8 inches. It's not 30, 40, 120 inches. So by the time we reach that point where the green curve is starting to hit the bifurcation theory curve, the amount of bending is not, like we're bending the column right around itself or anything like that. It's still, for the column that I demonstrated, it was still on the order of 6 to 8 to 10 inches of lateral bending deflection halfway up the column. All right. So that's what we're seeing is that my point is that the column, it's only theory to say that the column is perfectly straight and then it was infinitely buckled. All right. That's my best try at that. Craig and I are going to hit this slide every lecture. So keep the questions coming out. I'm hoping that adds some light to it. If you went to slide 12 in your deck there, Nate, I think you can see one of these columns experimentally being tested. Is there a way? Am I alive here? Can I do that? Oh, yeah, here we go. Oops, we just did it. So on the left, yeah. So on the left, this column is had its day. All right. So the column had an initial imperfection, something on the order of ln 1,000, and at first you couldn't see anything. It looked straight, and now finally those people measuring, they can see a column that is flexing. The deflection in that column looks to me somewhere on the order of 2 or 3 inches mid-span. They might run the test a little bit longer, but that column is spent. All right, so that's what we mean by that. And that green curve will slowly approximate, if it's elastic buckling, will slowly get closer to the Euler pi squared E over L squared term. So I give it a try at that.
All right. So we're going to move forward to slide 24, and this is the slide that this question was asked upon. Now, you mentioned this issue a few slides down the line, but this person was looking at these numbers and wondering about what would the location of supports within the cross-section, for example, an eccentric support with respect to the center of gravity of the section, how would that affect the buckling load?
Okay. All right. I'm going to need you to repeat it, but let me start with how this column was supported. It was basically supported top and bottom so that it couldn't twist and it could not move in any direction except where it was permitted to be squished. So those are the conditions. Now, the person asking the question wants to change the support conditions in some way. And how did they want to change them?
They want to offset them from the center of gravity of the section. So I think just looking for what would happen if this were the boundary conditions were eccentric or the load were eccentric.
Okay, now I see where you're going. Okay, so what's going to happen here, and we're actually going to take a look at this when we look at beam columns a little bit later. But at that point, what you're going to do is put some bending into that column. And what that's going to do, if we're out there in the elastic area, is the bending is going to cause some significant deflection to occur. And that's why we don't allow you to go all the way up to sigma capital E there, but only up to alpha times sigma E, because the bending is starting to get pretty significant. So if you have a small amount of bending, you're going to get a deflection mid-span, and the column's going to flex. And as you put more and more load on there, the bending's going to get big, the deflections are going to grow, and if you let it, you'll actually get yielding. You'll yield the column even out there in that elastic range due to the combination of axial force and bending. But the deflections really start to grow when you are under massive amount of compressive force, and it doesn't take much bending before you get a deflection, a flexural deflection that's really running away.
Yeah, so Ron, I think also the questioner is asking about the support condition. I mean, normally, when we're drawing our free body diagram for that pin support, we put those reactions, the lateral reaction, right through the centroid of the column. Let's say if we were just to grab a flange instead of grabbing right in the center of the web of the wide flange shape, would that offset affect the load the column could hold?
Oh, for sure. The further we go away from that centroid, the more we're going to impact the column force. Yeah, it's the same impact that initial imperfections are having. They're driving down the amount of that the column can hold. Now, when you're way out in the slenderness range, LNR of 200 or something like that, I think it's more of a chicken out factor. The column is flexing so much that you just want to get out of the way. The column is literally failing before you. But yeah, the way we would solve that problem is I would take the axial force and I would still drive it through the centroid, but I would accompany it with a moment. And I think I have that in slide, let's see, this slide here. On the right, the test that I would do as I get concerned about that eccentric loading is that the mass hand test or whatever you're doing would have both the axial force going back through the centroid. I'm looking at the column on the right, and I would also apply a bending moment up there to account for that eccentricity that the axial force was placed at. And sure enough, that'll eat away at the strength of the column.
All right. Well, thank you, Ron and Craig. Unfortunately, we're a bit over time now, and so we're going to go ahead and end things here.